So let's talk a little bit about retrosynthesis. This is probably one of the more challenging problems that you'll have to deal with in organic chemistry. Now, in retrosynthesis, we have to define a couple terminologies. First of all, we're going to have a target molecule, and that's just the product that you want to end with. I don't know why I didn't finish that here. I guess I said the product you want or you want to end with. Meaning after the course usually of several reactions. And then you have the starting material, and that's typically there's an organic molecule that you're told you need to start from, and that you're essentially transforming that molecule reaction by reaction into the target molecule. Now, typically, you'll see a retrosynthesis problem given in this way, where you'll see this kind of double arrow, this kind of bold double arrow, in which the item that's on the left side, and you have to be careful about this as it's going to be opposite of what you might expect. The item that's on the left side of the arrow, that is the target molecule. In other words, it's the final product you want is on the left side, and on the right side is the starting material. So you just have to watch out for this unique symbolism. Many students get it reversed and they completely mess up the problem because they're trying to make the target molecule turn into the starting molecule. But what you're really trying to do is you're trying to find a pathway of reactions that will take the starting material with a series of reagents, 1, 2, 3, etc., that'll transform it into the target molecule. So let's take a look at this retrosynthesis problem. Excuse some of the racings. I went through various ideas of what my example should be. But what I finally ended on was this is our target molecule here, and this is our starting molecule. And the key to success in this problem, as is many times in organic chemistry, is don't panic. Because you need to think methodically through this. And so you need to just kind of compare and contrast the molecules. What's different? What's the same? So one of the aspects that's the same is you do have this piece right here that's a cyclopropane and then a carbon coming off of it. That's the same piece right here in the starting material. So at that point, that gives us an idea. I need to do something to the starting material that adds this stuff here. And in the course of it, this bromine is going to disappear. Now, try not to think of this bromine as shifting over, because we never learned any reaction where bromine shifts over. We've learned how to add bromines, and we've learned how to replace bromines, and we've learned how to eliminate bromines. And by replace, you can use a different word, substitute. But we've never learned how to shift them over. So you're going to probably have to do a couple of reactions. But one of the first things that should stand out is you also have 2 additional carbons. You have an additional carbon chain here. And that's one of the first things you should point out to yourself as you compare. I need to add a chain of 2 carbons to this molecule. And lucky for you, this semester, there's only one carbon growth reaction that we've learned. The second thing you need to do, and it won't necessarily be just 2 steps, or 2 stages, I should say, or 2 sets of reagents, it might be a couple, is you need to still have a bromine by the end, but at a different site. So let's think a little bit about this on how we can do it. So like I said earlier, there's really only one reaction that we've learned about that connects or extends or combines 2 carbon chains. And it may be you're not used to seeing it in this manner, and so that might throw people off. But let's take a look at that example. And the example, if you don't remember, was taking a terminal alkyne and adding an R group to it, a new R group to it. And so I got these cards that I always like to write. You flip it over for a little more detail here. And what you did was to a terminal alkyne, you add sodium amide, which transforms it into an acetylide ion. And then the acetylide ion you combine with an alkyl halide. Now, keeping in mind that the alkyl halide has to be primary, but this is what we just learned previously like a lecture ago or two. Actually, it was the last lecture. Now, what we're not used to is we're not starting with the acetylene. And so one of the ways you can do this is you can imagine that I just add, and this is where you get to be a little more freeform than most other problems on organic. You can just assume you have access to the chemicals and classware necessary to prepare and then add this to something that happens when you add an alkyne to sodium amide. So you're not going to put sodium amide because that is going to mess up with this molecule. You need to already have prepared the acetylide ion. And so essentially you need to imagine the piece that you want here. And if you don't realize what it is, you want to do the reaction that adds this triple bond to it. Why this triple bond? Because remember, our target molecule has 2 additional carbons on it, and now this molecule has 2 additional carbons on it. So how do we create that? Well, we need to add sodium acetylide. This. And remember, the sodium carbon, what this essentially means is sodium plus and the acetylide ion. Not that you draw that in the actual answer, but that's what that is. And so that will add this to this primary alkyl halide, and the bromine will fall off. But you don't have to write that in a retrosynthesis, but off to the side some bromide. In fact, you form sodium bromide technically, but we don't write that. So that's the first reaction. We've made this. Remember, our goal though is to make this molecule. So we obviously don't want that triple bond anymore, and we want to add a bromine. But we have learned that we can add bromines to pi bonds. And in fact, the following lecture from this one, from this Tuesday lecture, but the one after Thanksgiving, we're going to talk about ways that you can add bromines to triple bond alkynes. However, those, as we'll see then, usually add twice as many as we learned about in alkenes. In other words, if you add HBr, you're going to add 2 bromines and 2 hydrogens. If you add Br2, you're going to add 4 bromines total, 2 for each pi bond, because it's going to behave twice as much as it did for an alkene. So we can't do that. It wouldn't give us just 1 bromine. The only way to add, target molecule, the only way to add 1 bromine, this is where now you can kind of think backwards. So I'm going to take a break from this, and we're going to think backwards. We're going to start with our target molecule, because we know there's something missing between these 2 stages. And our target molecule has a bromine here. How do we add a bromine to 2 carbons if it wasn't there before? The only reaction that we've really learned that does that, so far at least, is, I dropped a card, excuse me. The only one that we've learned so far that adds a bromine to carbons that wasn't there before is a 1 bromine to it, is hydrobromination, where you add an HX across a double bond and you end up adding the X and the H. Now there's no stereospecificity or selectivity. It adds to both sides, but that's okay because we didn't say anything about stereochemistry. But the important thing is it adds at Markovnikov. The X ends up on the more substituted carbon, not on the least substituted carbon. And the reason why that's insignificant is because if we add a bromine to the least the less substituted carbon, it would end up here. So we want to, now this is where I'm going to use that backwards, or that double arrow again, because remember, this is actually a product that we're trying to get. And a very likely way that we can make this is from a double bonded carbon by adding bromine, hydrogen bromide to it, HBr. So the question is, how do we go from here to here at that point? And oftentimes as you're doing, especially if you start working backwards and you're working forwards at the same time and you're trying to link them, you don't know if it's 1, 2, 3, 5 steps. You try to make it, that's the goal, to make it as short as possible, the limited steps as possible. But it could be maybe you need 2. Now this one, it turns out we only need 1 at this point. We only need 1 step because we know, at least for this Tuesday's lecture, that there is a way to take a triple bond and turn it into a double bond. We can reduce the triple bond. And we learn 2 techniques. We learn one way that you can end up with a cis double bond and another way you can end up with a trans double bond. However, in this case, it doesn't matter because, well, one, this is a CH2, so there is no cis and trans or E or Z. But also, even if there was some of that, since our final product doesn't really, since our final product, what's I gonna say? Since our final product, we don't stop at the double bond, it doesn't matter whether you have a cis or trans double bond. If you add HBr to it, you're always gonna get the same thing. So it kind of doesn't matter. So we can at this point pick any of those choices. Let's just say I'm going to use the one that ends up with a trans alkene. Once again, not that that matters because you won't get it, but that is the one that you end up with a wait, that's not it. With a trans alkene. So an E alkene from an alkyne. What is that? Dissolved metal reduction. We have sodium and ammonia. And then you end up with the trans. Like I said, you can also do the one that you end up with the cis, which is the poison catalyst reduction, where you have hydrogen gas and a Lindlar's catalyst. So in the end, since that is the reagent that would take us from here to here, what's our final product, or answer, I should say, look like? Starting with our starting material. And an arrow ending in our final product that we wanted to get. We write them all in these numbers, these stages. So first we would add sodium acetylide, I think it's called acetylide. Then we would add a sodium metal dissolved in ammonia to reduce it to the alkene. And then we would add HBr. And we've done a retrosynthesis. I think the biggest challenge for students is you want to be able to look at it and know the right answer right away. And unfortunately, with retrosynthesis, it always requires some critical thinking and digging through your toolkit of reactions, looking at things and trying to tie them together, trying to find a link where you can take a triple bond and add to it, or to reduce it then to an alkene, which can then be transformed into a halide. Well, here we go on our adventure of retrosynthesis. But as you no doubt will continue to have questions as we lead up to the final exam, in which there will be at least one retrosynthesis problem, definitely ask me as we go along the way. I'll try to occasionally throw a few problems at you, maybe in lecture or maybe during office hours if you continue to have questions, or as extra credit for your last couple of homeworks. And that way you can try to get a bit more practice as we go along. Well, hopefully in lecture, if we get to this in lecture, we can discuss even further. Thank you. I'll see you later.